In this video, we go through mechanics and problem solving related to thermochemistry. We want to remind ourselves of some basic definitions. E is the internal energy of a system. It's the energy of all the particles, the sum of their potential and their kinetic energies. And we can't quantify the absolute value of internal energies, just like we can't quantify the absolute value of enthalpies, but we can do differences. And as we traverse a particular reaction profile or process profile, we can see a change in internal energy of the system. And the change in internal energy of the system as it goes through a pathway is manifested as heat, either heat absorption or heat release by the system, and work done on or by the system, both of these in relation to the surroundings. So we have delta E as Q plus W, and our basic sign convention, which helps us to understand where we're headed with this. Delta E being positive means internal energy goes from the surroundings into our system. Delta E being negative means internal energy goes from our system into the surroundings. In parallel with the sign convention for delta E, we have the same sign convention for Q and W. If the system releases heat during the process, then Q will be negative. If the system absorbs heat from the surroundings during the process, Q will be positive. If the system has work done on it by the surroundings during the process, the work will be positive. And if the system does work on the surroundings, then the work for our system will be negative during the process. Now let's take an example to illustrate this problem or this approach. So we have a chemical reaction. Iron solid reacts with acid to produce iron 3 ion and hydrogen gas. The reaction as written is a net ionic equation, and you would recognize this as a redox process. So this is a redox process. We would have identified this as a displacement reaction back in chapter 4. And this reaction is already balanced for you. There's a fractional value for the hydrogen. That's just the way this happens to be written. If you wanted to make it whole numbers, you could put a 2 in front of the iron, a 6 in front of the hydrogen or protons, 2 in front of the iron 3s, and then you'd have 3 moles of hydrogen gas. So when you carry out this reaction, you release hydrogen gas. So the hydrogen gas is going to push against the atmosphere. So during a particular reaction, the system releases 5.1 liters of gas at standard temperature and pressure. There's a variety of calculations we can do on that. We won't do those now. In this case, the system pushes against atmospheric pressure for a total of 503 joules of work being done during this process. The system also heats up during the reaction, but then it releases the 299 joules of heat from the reaction. As the system returns to thermal equilibrium, it releases the heat to the surroundings. So let's ask the question, what is the total energy change of the system during this process? So we want to know, what is the internal energy delta E change? You can go ahead and solve this one on a piece of paper if you have it, and then continue the video in a moment. Here's our solution. First, the system does 503 joules of work. Therefore, W is minus 503 joules. The system heats up, but it's not pulling heat from the surroundings. It's actually heating up from the reaction exothermicity. And it releases 299 joules of heat to the surroundings as the system returns to thermal equilibrium. So Q then will be negative 299 joules. So we take sum of those two values, and we end up with negative 802 joules. That's the change in internal energy for our system during the process. We discussed enthalpy. We understand enthalpy is given by H equals E plus PV, and during any process that has only PV work, and for cases where the pressure is constant, we see that heat at constant pressure is what is equal to enthalpy. So we said last time enthalpy is sometimes expressed as heat at constant pressure. That is one way of thinking about it, and enthalpy can generally be more than this under other conditions, but at constant pressure, enthalpy is the heat of the system during the transition. And of course, we looked at a variety of cases where we look at delta H values. In general, if we're going from reactants A to products B, or state A to state B, the change in enthalpy for the process is the enthalpy of the final state minus the enthalpy of the initial state. So we'll continue on. Here's a table of standard enthalpies of formation. These are how we're going to get the individual states from which we will derive our changes in enthalpy. Of course, you wouldn't know all these numbers. You would know all of the elements and their standard conditions because you know those are all zero. For your exam, you may have a much more extensive table depending on what sorts of problems we work on, but they'll all look very similar to this. You will have an enthalpy of formation, typically in kilojoules per mole, and you'll have the composition, either the element or the compound, and then the phase will be written in parentheses. Let's take a simple problem. What is the standard enthalpy for the following reaction? Calcium carbonate solid goes to calcium oxide solid plus carbon dioxide gas. Standard enthalpy for the reaction of this is what we will calculate. Then we'll ask ourselves the question, is this reaction exothermic or endothermic? This is a very important reaction. It's done on very large multi-metric ton scale every year. It's important for production of industrial base. Calcium carbonate is the primary constituent in limestone. Calcium oxide is what is sometimes termed quicklime. It's the cheapest industrial base, strong base that we have. Now, if we're going to do the calculation, we know that we need delta H0 of formation for the products minus delta H0 of formation for the reactants. So let's go back up to our table. We're going to need calcium oxide, and we can see in the upper left-hand corner we have calcium oxide. Right below that we have calcium carbonate, and then down a little ways we have carbon dioxide listed. So we'll use those three values for delta H0 formation. Plugging those in, as shown here, we take the sum of all the products, so negative 635 plus negative 393. We add that together, we subtract off the reactants, and we end up a value of plus 178.3. And since this value is positive, this reaction is endothermic. It requires heat, requires energy to drive this. And this makes sense consistent with what we know about calcium carbonate. Limestone is a very stable structure. It's been around for geological time scales, the cliffs of Dover and many other calcium carbonate structures throughout the world. And in the industrial process to produce quicklime or calcium oxide, it's done in large furnaces. So large amounts of calcium carbonate are put into the furnace, heated to high temperature to drive off carbon dioxide to produce the calcium oxide. Let's do another problem using this approach. What is the standard enthalpy for the following reaction as written? In this case, we take 2 moles of silver plus 1 mole of chlorine gas to produce 2 moles of silver chloride solid. What is the delta H for this reaction? And then, is the reaction exothermic or endothermic? In this case, again, we'll take the enthalpy of formation of the products minus the enthalpy of formation of the reactants. We can get the values from the table that we looked at a few moments ago, but it's important to remember that the stoichiometric coefficients in front of each species must be included. So our reaction will, enthalpy for reaction will look like this. 2 times the enthalpy of formation of silver chloride, which is negative 127 kilojoules per mole, is our products expression. And then we subtract off the reactants. Both of those are elements, and they're both 0. The 2 has been included for silver. 2 times 0 is the same as 0, but that's just a reminder that we need to use all those stoichiometric coefficients. So we end up with this value for delta H0 for reaction. Now it's important to note that this is negative 254 kilojoules per mole for this reaction as written. And we'll see this come into play in our next video in part 2 on mechanics for chapter 6. But it's important to remember this is as written. If we change the stoichiometry, so for example, if we used 1 mole of silver solid reacting with a 1/2 mole of chlorine gas to produce 1 mole of silver chloride, our final result would not be 254, it would be negative 127. Based on the reaction exothermicity, the enthalpy of reaction, we can identify the reaction exothermicity. It's negative, so it's an exothermic process. Heat is released in this reaction. We'll continue on looking at calorimetry and heat flow. Here are specific heats, specific heat capacities for a variety of elements, compounds, and different materials. These are, for example, wood, cement, and glass. These are average values because there are different types of glass. Cement and the wood would depend on how it was generated and how long it had been drying and other things. And we have our calorimetry equations that we remember. These are important equations to remember. Q is equal to Cp delta T. Q is also equal to mCp bar delta T, where Cp is the heat capacity and Cp bar is our specific heat capacity. Now let's look at a problem addressing heat flow. In this case, we will look at a piece of metal that will cool down from a high temperature to room temperature. We have an 8-gram piece of gold at 400 degrees Celsius, which is cooled to 25 degrees Celsius. What is the heat flow in the gold system? Next, how much water at 20 degrees Celsius is required to thermally equilibrate with the gold in order to accomplish this? So what we have is we'll have a gold piece at 400 degrees Celsius, put into water at 20 degrees Celsius. Heat flows out of the gold into the water. So the Q for gold will be negative. The Q for the water will be positive. And the system will equilibrate at 25 degrees Celsius. Let's approach the first problem. In this case, Q for the gold is equal to the mass times the specific heat capacity of the gold times the change in temperature. And in this case, the final temperature is lower than the initial temperature, so the temperature change will be negative. In this case, the mass is 8 grams, the specific heat capacity is 0.129 joule per gram Kelvin, and the temperature change is negative 375. Therefore, the heat flow associated with the system, gold, is negative 387 joules. The next question is how much water is required to absorb this amount of heat over a 5-degree temperature change? So Q for the water will equal it'll actually be equal and opposite to the Q for the gold, but in this case, we'll just take delta T as a positive value and Q for water is a positive value, and we'll look at the magnitude of the Q for gold. We take M times specific heat capacity of water times delta T. In this case now, we know the heat for water. So Q water will equal 387 joules. It is absorbing all the heat from the gold. We don't know the mass. We know the specific heat capacity, and we know the change in temperature. Here we have these values. We then can go and solve for the mass for the system. M then is equal to 18.499, which is 18 grams to two significant figures, which is what the problem would require. Now we understand the basic heat flow problems. In our next video, we'll look at more complex calorimetry problems involving chemical reaction processes.